Swayam Prabha. Digital India. Educated India.
Is going to be somewhere here. Right? So whenever there is no current, I'm going to have the battery voltage directly showing up at the cathode of the diode. If there is no current, it's open circuit. So obviously the cathode of the diode will have the same 230 volts. So only when the anode reaches 230 volts, it can have any conduction. Otherwise it cannot have any conduction. The diode can start conducting only when the positive voltage here reaches 230 volts. So it cannot conduct until this portion. The diode will not be able to conduct until the anode also reaches at least 230 volts, ideally. So the current can start flowing only from here. Got it? The current cannot really flow before this because the diode cannot be forward biased before this particular voltage, AC voltage, reaches 230 volts magnitude. So the current will start flowing at this point. If I write the equation here, I have to write when it is conducting Ri plus L di by dt plus E equal to VAC. This is when diode is conducting. When the diode is conducting, this is how it is going to be. Right? So the current will start flowing from this point. Now look at the work of this VAC. It has to now take care of three things. One is the resistance drop. The second one is inductance stored energy. The third one is snubbing E. Because E is not going to allow conduction very easily. It is opposing the current. So it has to take care of all these three things. Only then you are going to have any rise in the current. The rise in the current is only because inductance is storing the energy. So I should say in this particular case, L di by dt is going to be whatever is VAC minus E first of all, and then minus Ri. So only when the voltage crosses 230 volts in the positive half cycle, it is going to start conducting, and then the current starts increasing. But at what point the current will reach peak depends upon when this whole thing is zero. So I am going to have probably a current reaching the peak right here, and then it might probably end up here or here depending upon how much is really the inductance stored energy. If the inductance is really dominating over the resistance, then I may have the current continuing for longer. Right? So now if I try to look at this as my value of current, so I can again draw IR. I can say what is VAC minus 230 volts minus IR. That is what is the voltage that is available for inductance to store energy. And after that I have to see how much is the voltage it will return. Right? So I want you guys to complete this exercise. Please draw the waveforms of VL, that is the shaded portion, and you try to get what is IR, and then you try to get what is VAC minus E minus IR. That will give you what is the inductance stored energy portion and what is retrieved. Please look at both of them. Right? So you are going to see that whenever you have an inductance in your circuit, you are going to have the current going beyond whatever, it would have normally gone. Right? So much so far half-wave rectifier. So now that we have seen half-wave rectifiers with diode R load, RL load and RLE load. Let us now try to take a look at a full wave. First of all, a center tapped rectifier. I think I drew it last time when I was probably explaining power supplies, but we'll take a look at this once again. We call this a center tapped rectifier because we will always use a transformer with the center tap. What we mean by center tap is, if I am going to have a transformer secondary like this, I am going to take from the midpoint a connection. So I am taking a tap from the midpoint, from the center. So we call this a center tap. So center tapped rectifier. And I am going to have basically a transformer which is supplying this voltage VAC. Right? And of course, because it is power, normally it will be iron core transformer. So I am showing the two lines to indicate that it is an iron core transformer. Now I will have one diode here and one more diode here. I can short these two and then I am going to connect a load here between the center tap point and this. Some of the books might have shown a load in between this point and this point, which is the same, exactly. Okay? So this is typically a center tap rectifier, and let me start off with the resistance load itself. Right? Let us say here the peak value of voltage is something like 325 volts peak. 230 volts AC I have taken. So this will be 325 volts peak. Now if I have a 1:1 turns ratio, for example, for the transformer, I should have here 325 by 2 and again I should have here 325 by 2 volts as the peak. Right? I should have half of the voltage as the peak value in either of the sides. Right? Whenever there is a positive half cycle, I am going to have plus here and minus here, because of which I will have again plus here, minus here. And if I am taking half the tapping, I should have had the minus point here for the upper half and again plus point here for the lower half. Right? That's how it will be, because it is series connected, series addition. Right? Like when we talked about auto transformer, we used to say series addition and series subtraction. This is series addition. So we are going to have plus minus like this. If plus is here, obviously this diode will be forward biased, but at the same time this diode will be reverse biased. So I'm going to have only this carrying the current. Right? Only the positive portion, for the positive half cycle, only the upper portion will carry the current through diode D1. If I may call this as D1, D1 will conduct during positive half cycle, only the upper portion of this particular transformer secondary will be active. Similarly, during negative half cycle, only D2 is going to conduct, which means I will have only the lower portion of the transformer being active, secondary side being active. So what I get across the load will be only 325 by 2 volts peak. Definitely not whole of 325. Right? You get my point? I will not be able to get exactly whatever is the voltage I am applying here, only half of that voltage will come at the output. I can't get full voltage unless I have 1:2 turns ratio or something. Right. And one more thing is, when this diode is conducting, this is going to be a short circuit. right? This is a short circuit, hardly any voltage drop. So I'm going to have essentially whatever is the voltage here, that voltage will come at the cathode of the other non-conducting diode. So I will get the same positive voltage connected at this point. And after all, this negative voltage is here. So I'm going to have the entire 325 volts with negative here and positive here coming up across the diode, which is not conducting. That is coming in inverse form. That is minus here and plus here. So the diode will not be able to conduct, all right, but the amount of inverse voltage or reverse voltage that is coming across the diode will be not V by 2 but full V. The output is only V by 2. But the voltage that comes across the diode is going to be the complete V, because both these windings, because if this is positive, this will also be positive and this is negative. So this voltage will be the complete VAC or 325 volts peak. So the peak inverse voltage rating, we call this as the peak amount of reverse voltage that the diode has to block. How much the diode has to block? Although the output what you get is VAC by 2, the amount of voltage that it needs to block during reverse biasing condition is full VAC, and whatever is the peak at that point in time. So you are going to have the peak inverse voltage rating of this diode is going to be VAC, whereas output is going to be only VAC by 2. Of course, I have to completely derive the expression for average value of voltage, which we have not done. So we are using a diode of higher value of rating, but we are deriving only a lower value of output voltage. What is the big advantage of doing this? Only there is one advantage. That advantage is whenever this is conducting, I have only one device conducting, and after that the load comes directly. So if one device voltage drop is 0.7 volts, I will have whatever is my output voltage minus 0.7 volts as the output. If there had been two diodes conducting like a bridge, which we will see eventually, we are invariably going to see that 1.4 volts are dropped, 0.7 plus 0.7. When you are talking about 5 volts power supply or 3.3 volts power supply, this 1.4 volts matters so much, because out of 3.3, if 1.4 is going away, then I get very minimal output voltage. Or correspondingly, I have to design the transformer secondary for a higher voltage. So whenever I am worried much more about the voltage drop, not about really choosing a higher voltage rating for the diode. So typically power supply applications. In many power supply application, instead of getting a 15 volts diode, if I have to get a 30 volts diode, the cost will not increase much. That's fine, perfectly fine. But I will be able to save on the voltage drop. Whereas if I am talking about a 6 kilovolt application, obviously I will not use a rectifier like this, because instead of 6 kilovolts, if I have to choose a 12 kilovolt diode, the cost will increase enormously and it may not be available. So center tap rectifiers are generally used only in the case of power supplies, not in any other application. If you talk about DC motors and so on and so forth, we will never use a center tap rectifier. Center tap rectifiers are generally the specialty only for power supply applications, right? One particular case I forgot to discuss with the freewheeling diode, half wave rectifier with the freewheeling diode. Let me take that up also, because this will come up repeatedly when we are talking about other rectifiers. That's the reason I would like to go for this. So this is my normal half-wave rectifier. I'm showing with RL load. We have drawn the waveform already, so I hope you guys are now somewhat familiar with this. Right? Let us say I'm going to connect a diode like this, which is across the load, which I would call as freewheeling diode, which will be able to take the trapped energy across the inductance. It will essentially pass the current because of the trapped energy in the inductance. So we call this as freewheeling diode. It is essentially simply going to circulate the current. It doesn't have any other job other than to do this. So let us say this is my diode, which is the normal diode, which is meant for rectifying the AC voltage into DC voltage. So here is my V load and this is my VAC. Right? So this is my supply voltage, and initially the diode starts conducting at this point. Right? And if we write the equation, we wrote it earlier also, Ri plus L di by dt equal to VAC when D is conducting. This is what we wrote earlier also. Right? Now, we will have obviously the current peak reaching somewhere here. I am drawing the current like this. So it has reached somewhere here. So if I try to draw the voltage, hopefully at this point, it should have touched whatever is the AC voltage. Right? So this is actually IR, whereas this is I. You get my point? So that is where it reaches the peak. And after that, the current is going to come down. We said that current will come down. Right? When it is coming down, right, I'll have to look at what happens to this diode. Does it come into picture at all or not? That's what I'll have to check. Right? When this was positive and this was negative, and when the current was decreasing, this became minus and this became plus. Right? And both of them put together was able to circulate the current in the same direction through the resistance load. Right? So if I actually look at it, I was having VAC plus L of di by dt, where di by dt was having a minus sign, equal to IR. This is what was happening. You get my point? This is what was happening earlier. Right? So I should say that maybe VAC minus, let me put minus into minus becomes plus rather. That is why I am saying that L di by dt is joining hands with VAC. Both of them together is circulating the current through the Ri. That's what it is. Now, when it comes into negative half cycle, when the current is actually, when the voltage is coming into negative half cycle, at that point, I am going to have actually, this is going to be plus and this is going to be minus in the reverse half cycle. Right? But as far as this is concerned, I am still going to have this as plus and this as minus, and this Ri was originally supplied by joining hands with both of them. Then I was having the power supply voltage also aiding the current circulation in the same direction as that of this, and then resistance was wanting to have a voltage drop in this particular direction because the current is still flowing in the same direction. The inductance was aiding it, basically. Now, the power supply voltage is trying to oppose the flow of current in this direction. Because of the reverse half cycle, this being plus and this being minus, if the power supply had its way, it would have had the current in the opposite direction. So obviously it is going to put up a stiff resistance to the flow of current in the same direction. It will not allow it to flow as much as possible. So if somehow this power supply can be bypassed, obviously the circuit will try to find another way. So under that condition, if the inductance stored energy is still dominating, because this is plus and this is minus for the inductance, this particular diode now gets forward biased and takes over. The moment this diode takes over, if I neglect the drop across the freewheeling diode, I should write the equation as Ri plus L di by dt equal to 0, which is actually the voltage drop across the freewheeling diode. So this is when DFW is conducting. When the freewheeling diode is conducting, I will get literally 0 voltage across the load. I will not be able to get any voltage across the load except 0 voltage, because the freewheeling diode is essentially short circuiting the RL load, right? So if I try to look at actually the voltage waveform corresponding to this, I am going to have until this portion a positive voltage, and after that it will be 0 voltage until the freewheeling diode conducts. I will not have any voltage coming into picture at all, right? So this portion is going to be due to freewheeling diode, whereas this portion is going to be due to D and RL load. Now, because it is 0 voltage that is coming up across the load, I am drawing the load voltage. This is V load. V load is VR plus VL. I have to add both of them, not just R alone or L alone. It is the summation of both. Now I have the freewheeling diode voltage coming up as 0. Compare with the previous case where I didn't have freewheeling diode. When I didn't have freewheeling diode, always the equation was this. But now with the freewheeling diode, the equation is this. So when I was looking at the case without freewheeling diode, I had VAC minus Ri equal to L di by dt. Right? When VAC was in positive half cycle, fortunately for me, it was actually aiding the inductance stored energy. VAC and inductance stored energy together actually made up for whatever is the resistance loss once the current started declining. But when this is reaching negative half cycle, in negative half cycle, I am going to have VAC also of the opposite sign. So VAC will also become a drain on the inductance stored energy, because that is also very actively opposing the flow of current. So despite VAC, despite resistance drop, the current has to be sustained by the inductance. That was the case when I actually had no freewheeling diode. Especially when the voltage becomes or comes into negative half cycle, I am going to have a stiff opposition from the supply voltage. I am going to have a stiff opposition from the resistance in the form of voltage drop or dissipation. So both of them are going to put up a stiff opposition. and still the inductance has to sustain the current. Whereas, when I have a freewheeling diode, this opposition is gone. I don't have the supply voltage opposing at all. Supply voltage is completely isolated. This diode is sitting here, D, which is not conducting anymore. It will not conduct anymore. Only thing that conducts will be the freewheeling diode. So, between the supply and the load, there is hardly any connection. No current is flowing between the supply and the load at all when the freewheeling diode is conducting. So, the opposition offered by the supply voltage is absent. In the absence of that opposition, this current can continue for a little longer. So, freewheeling diode cases, normally the current can continue for longer because the opposition is somewhat decreased as compared to what we had in the previous case without freewheeling diode. Right? So, this will be the kind of current continuation that will take place, and for getting whatever is the value of beta, we have to use this equation, Ri plus L di by dt equal to 0, not equal to VAC beyond pi. Right? So, correspondingly, if I try to look at what is IAC, it becomes somewhat different. It will not be the same as what I had as the load current. So, if I try to look at what is IAC, I am going to have only until then, until this portion, until pi, I will have the diode carrying the current. The main diode D will carry the current until then, until pi. After that, only the freewheeling diode carries the current. So, I will have the current to be somewhat like this, and then it comes down, and then that's it. Abruptly it comes to 0. This will be IAC. After that, whatever is the current that is coming up, this is DFW current. You get my point? So, AC current happens to be different from the load current whenever I have a freewheeling diode. It is definitely going to intervene in the conduction, take away all the current, depriving the supply of any current. It is discontinuous. You can see that abruptly the current comes down to 0. And here abruptly the current rises. Whatever is going through the load, that is continuous. Initially that current was being supplied by the D from the supply. Later on it is continuing because of the inductance, but it is freewheeling through the diode. So load के लिए कुछ फर्क नहीं पड़ता है. It doesn't care. Wherever the current has to go, it will go. But the load current is continuous. There is no discontinuity. I should not say continuous because it comes only until here. Again it will start. In that sense it is discontinuous.
Basically at that point the summation of the two currents will be continuous, right?
Yeah. So whatever this leftover, that current should come here. So if I say that this is some I1, this has to be the same I1, no doubt. Why is it? It is happening at value pi because until then this fellow was not opposing. This fellow was also aiding the current. As long as this fellow was aiding, there is nothing to really look for a smaller resistance path. This fellow was not opposing, so it was not really offering resistance. Now, this particular fellow is also opposing. So, might as well look for a path where least opposition will exist. That's what is happening. Right? Okay? So much so for diode rectifier. We have still not seen the full bridge rectifier. We look at the full bridge Then we will go to thyristor. Okay? So we are going to call this as uncontrolled bridge rectifier, which is only with diodes. So we call this as uncontrolled. Right? So I normally draw it like this. I am sure you would have learnt it sometimes differently with diamond kind of structure and so on, but doesn't matter because this is easier for us, especially when we are going to go to three-phase rectifier. So I would like to draw it somewhat like this with the load here, right, and power supply at this point.